So, in continuation of the last video, without further ado, I will tell you about these Euclid numbers. Now, as it turns out, the first 5 Euclid numbers are indeed prime, so they're Euclidean primes. And the next 5 are composites. And in this video, I wanted to show you a few appendices that would help illustrate these Euclid numbers. So what we have here are the first 10 Euclid numbers. So here we have n, which serves as the index, e sub n, which serves as the, which is just the nth Euclid number in this column. We can see its construction, which is simply, 1 plus a product of prime numbers, specifically the first n prime numbers. And then in the final column, we have the prime factorization for each of these Euclid numbers. And obviously, if I have a p there, that indicates a Euclidean prime. So, as you can see, the first 5 Euclid numbers are indeed prime numbers, and the next 5 are composite. But these figures might help demonstrate, among other things, that the Euclid numbers that aren't prime have interestingly large prime factors. Prime factors that are well outside the first n primes with which we started. So, for instance, if we go with e sub 8, we know it's built from the first 8 prime numbers, so all the way up to 19, but the lowest prime that actually divides it is 347. So that's very interesting how we can get such a disparity there in certain cases. And perhaps that's not too surprising, given Euclid's proof that I showed you earlier. If the Euclid number is composite, then obviously these prime numbers for these 5, these last 5 ones listed here, are going to be outside, these first n prime numbers. It's going to be outside of those, obviously, but what's more, I actually wrote a program that generates these Euclid numbers, and you can see here the more extended table up to about index 15. And this was the result that it printed to the console. So, this is a Java program, and basically I'm just showing you the same kind of table where we have n, the index on the left-hand column, going from 1 to about 17 or 15. And in this middle column, I have a p to represent whether it's prime or not. So that's the same idea, and I was able to program that into a separate method. However, at this point, the value of the Euclid number grows so large that it exceeds long.max value. This is after n equals 15. So you can see, if you look more specifically down here, it exceeds long.max value, which is about 2 to the 63 minus 1, or about 9.22 times 10 to the 18. So that's a very special number in this case, because I was using longs. I was using a data type called long in Java, and the program I wrote, even using a 64-bit integer, the largest possible data storage for a primitive type in Java, I could only calculate the first 15 Euclid numbers without running into, or, until I ran into this problem where it exceeded the maximum value possible for storage, and so I get this negative value, which is obviously false. Obviously, after 15, this program breaks down, and it can't calculate them accurately anymore. And in fact, even using Microsoft Excel, which I'll show you here, I used an Excel spreadsheet in order to calculate these Euclid numbers. But even here, I could only manage to get an estimate for these later numbers. If you zoom in, oh, well, actually, I guess I can explain this first. n, we have that same column, n, just the index, and then e sub n, the nth Euclid number, being on the right column, and the leftmost column is just basically a set of primes that I entered in there just by hand in order to help me develop the algorithm in Excel. But basically, if we zoom into the ones later on, like the indices 13 onward, actually 14 and onward, we see that the computer had to leave more and more digits as zeros at the right-hand side of these Euclid numbers, as you can see. And this is obviously false. We've already demonstrated in the prequel video that each of these Euclid numbers must end in a 1. So we should be seeing more, if we saw more digits, then each of these would also end in a 1. But the main point of this is that, Microsoft Excel evidently gives us a nice sense for the magnitude of these Euclid numbers as the index grows larger and larger, but evidently it doesn't give exact values after n equals 14. But that's okay. I'm not trying to discredit Microsoft Excel. I mean, at least we get kind of a sense for the order of magnitude for these numbers, so that's certainly a benefit. But that being said, it's interesting to see that that's all that it does, is give an estimate, the first few digits of these Euclid numbers. And I also wanted to show you give you a sense for the exponential nature of these Euclid numbers, and that is simply that we can see them in a scatter plot. And actually, I'll show you this one first. These are the Euclid numbers given in a scatter plot. So these are the first 10 Euclid numbers, and this x-axis here is obviously representing n, so the index, and then I've just plotted on a scatter plot the Euclid number. And so you can see, you might not be able to see it that well with this graph axis, but I'll show you another one in a moment that's improved. But the main point here is that it does have a fairly exponential trend line that has a fairly high r-squared value, 0.9784. And then if we go further down, we can see this one, which is adjusted. You can see that the vertical axis, the y-axis, has a log scale in it. So, adjusting the scale, we see that these points in the scatter plot, and this one is perhaps even more accurate because it uses 20 Euclid numbers, or at least approximate Euclid numbers, based on that estimation that I showed you from the table right here. But of course, the idea is that we're just, adjusting it and making the graph look linear by adjusting making the vertical axis a log scale. And, that is indeed what happens. That r-squared value actually went up a fair bit here when we used 20 Euclid numbers rather than just 10. But it's still interesting how we can get them all to line up and show how it really is of an exponential nature. So I wanted to show you all of that. Let me know if you have any questions. But other than that, I expect that in the next video, the sequel to this one, we'll be exploring the number of prime numbers that we skip over as these numbers grow larger and larger. And I suspect that we may see some other interesting properties, probably related to the prime number theorem. So thank you all very much for watching. I appreciate it very much. This is AllLogarithmsEqual. I'll see you next time.